Let us look at the next chapter, sampling distributions. Suppose x is a discrete or continuous random variable and say that this is the population. In other words, the probability density function or the probability distribution function. So suppose this for this random variable or for the population, the mean is mu and the standard deviation is sigma and the variance is sigma square. In general, we do not know these population parameters. So we want to estimate those parameters like a mu, sigma, sigma square, or something like a functions of those quantities. Say for example, sometimes you want to estimate mu divided by sigma. Or the other way, say for example, sometimes you might want to estimate something like a quantity, the random variable is greater than a certain number. So in other words, say for example, like the area more than that. Like what is the chance that something is going to last more than 100 months or something like that. That goes with this area. Okay, so the bottom line is we want to estimate mu, sigma or sigma square or functions of that. So of course we have to have a random sample out of the population and then we use that random sample to estimate those parameters or functions of parameters. Say that this is our random sample x1, x2, xn. Sometimes it's known as a simple random sample. In other words, there are other complicated ways to pull random samples, but we are simply looking at a very simple random sample. Okay, so once we pull the random sample, we are going to calculate a quantity out of that random sample. Say for example, if you want to estimate mu, so your estimate could be the average. Add them up and divided by n. So in other words, so it's a function of your random sample. So any function of your random sample is known as a statistic. So the quantity you calculate from your sample. Okay, so it's a statistic. So in other words, if you are interested in estimating mu, x bar could be a good estimate. Or maybe if you don't like your x bar, maybe you can look at the median. Or you can look at the highest 5% of the values and the lowest 5% of the value. You remember that we were looking at trim mean. So like throwing the higher extreme values like that. Okay. Or the other way, if you are interested in estimating sigma square. So this is a kind of a good estimate. You already have seen that one. Sample variance or the square root of that is a good estimate for the sigma. Okay, so anyway, the point is that, so when you pull a random sample, say, let us look into x bar first, okay? So if you pull a random sample, you will get one value. If you pull another random sample, you are going to get another value for the x bar. If you pull another random sample, you are going to get another value for x bar. So in other words, every time you pull a random sample, you are going to get different values for the whatever that statistic. So in other words, that quantity itself is a random variable. Depending on your random sample, you are going to get different values. So what we are going to look at in this chapter right now is the probability distribution. So probability distribution of that random variable. Okay, so in other words, the probability distribution of that statistic, whatever the statistics you are looking at, either that or that, is known as a sampling distribution. So when you say sampling distribution, is the probability distribution of a statistic. It's depending on what you are looking at. If you are looking at a probability distribution of x bar, it's the sampling distribution of x bar. If you are looking at the probability distribution of s square, then you are looking at the sampling distribution of s square. Say for example, if you want to estimate that, kind of you might think that, how about replacing this thing by x bar, the mu by x bar, okay, this one by x bar, and I'm going to replace this thing by s, okay. So that might be a good estimate, okay, we don't know, it might be a good estimate. Anyway, if you are looking at that kind of thing, the sampling distribution of whatever that quantity is, the sampling distribution basically of that statistic. Okay, so then first we are going to concentrate on X bar, and then if you have time, then we will look into these things probably towards the end of this course. Okay, so sampling distribution of X bar. So I'm going to give 3 theorems. So first theorem goes like this. Suppose X is going to follow a normal distribution with mean mu and the variance sigma square. So the mean and the variance, in general, they are known parameters. So whether they are known or not, the thing is that if you pull a random sample out of that, so suppose you are going to look at the X bar. So if you look at the X bar, which is the sum divided by the sample size, so this theorem says that if this is going to follow a normal distribution, the X bar, the sample mean, will follow another normal distribution with mean is going to be exactly same as the original mean, this mean, but the standard deviation, the variance is going to be this variance divided by n. Okay, so in other words, if you're looking at the standard deviation, so it's the square root of that. So sigma divided by square root of n. In other words, this standard deviation, which is sigma divided by square root of n. Okay, so in terms of the standard deviation, but in terms of the variance, this variance divided by n. So what this theorem is that if this is a normal curve, that's going to follow another normal curve and with centered around the same value, but the variance is less. See, remember that when you divide the variance by square root of n, this number, the whole number is going to be small. When the variance is small, meaning that the whole thing is very close to the center. The variance is small. You are dividing by a big number, right? So the variability is much less compared to this curve. So it's centered around very close to the mu value. Okay. So in different words, expected value or the mean value of X bar, expected value of X bar is that mu, and the variance of X bar, so is going to be original variance divided by n, or the standard deviation of X bar, original standard deviation divided by square root of n. So in different words, with this, when we say it like that, this is the variance, which is sigma square of X bar. Okay, variance of X bar. So this is the standard deviation sigma of X bar. Okay, so over here, basically when you write the sigma square, over here you are saying that the variance of X is sigma square. Okay, so this is the variance of X bar. So that is the first theorem. So here the condition is that if this is normal, this is normal. Regardless of the sample size, n could be 2. Even if you pull a random sample of size 2, this is still follow a normal curve. Okay, because this is already a normal. So the next theorem is somewhat, this is the same, almost kind of similar to that. But the thing is that what this theorem is saying is that if this is any random variable, okay, any random variable, so with mean mu and variance sigma square. The difference between here and here, I did not say that that is normal. Here we said that is normal. In other words, a curve like that. Okay. If you pull a random sample out of this kind of population, if you figure out the X bar, so this theorem says is this: the mean of X bar is going to be exactly same as this mean. Mean of that. In other words, this is the mean of X bar, is mean of X bar, or the expected value of X bar is same as that, and the variance of x bar, so in other words, the sigma square of that is going to be the original variance divided by n. So in other words, these two parts actually, these two parts here, this one and this one. But what we did not say is that this part. So since this is not normal, so this could be something like that with a little bump here, whatever that, something like that. But it's not normal. But the mean and the variance will follow the same thing. All right. So that's that. So the next part of the theorem, that's what the important part. Okay. So over here, doesn't matter. This could be discrete. This could be continuous or whatever that. Okay. But as long as this is the case, this is good. So the next part of the theorem, which is known as the central limit theorem, what it says is that for large n, if your sample is quite big, large n, the distribution of x bar, the sample mean, is going to follow a normal curve in addition to these two things. Okay? In addition to these two things. So in other words, so regardless of that, for large n, this will follow a normal curve with the mean mu and the variance sigma square. Okay, standard deviation is going to be the square root of that. So so this is very important because we did not say anything about that. Okay, so this is the next theorem. So the next theorem goes like this, central limit theorem. So if say this is a population with a mean mu, sigma square, the variance, if you pull a random sample, this is the only condition. This mu got to be finite. In other words, it should have a value. Sigma should be finite. If this is the case, if you pull a for large n, the distribution of x bar is approximately normal with mean mu, the variance sigma square over n. So in other words that. So this is true large n. So in other words, what we are saying is this, larger the n, better the approximation. When n is getting big and big and big, so this is getting closer and closer to this x bar, the normal curve. Okay, the rule of thumb is that when we say the large n, rule of thumb is that if x is, this one is a continuous random variable or the values are continuous values, so then rule of thumb is this is not exactly correct. It's got to be at least something like a 30. The larger then better the approximation, but you will see that later people look into that 30 as a okay value. Sometimes may not be okay, but in most cases if it is continuous, that is okay. Okay, so that's the rule of thumb. So in other words, mathematically you can prove that the statement is correct mathematically. So that's why this is a very strong statement. So this mathematical statement is this: if the x bar minus the mu, you are getting rid of the mu, and divided by the standard deviation, the limiting distribution of that is normal, standard normal curve, z curve. So in other words, this limiting mean, you may not know this one. If you have taken calculus, you might have seen this limiting thing as n goes to infinity, mean the sample size goes to infinity. The larger the n, better the approximation. Okay, so when n is getting large and large and large, this curve, the curve of this thing is getting closer and closer to that. So that's why this is a very, very important theorem. So even if we do not know anything about this, we can approximately figure out probabilities because we already know how to utilize the z curve. We can read those probability tables, okay? Z curves. So the next I will look into several examples with the central limit theorem.